Okay. Good afternoon, guys. So we shall continue. So what we did last time, we looked at the ways of calculating the dynamical matrix and therefore obtaining phonons using ab initio methods. And we considered the method which is called frozen phonon method. And that method requires performing one-point calculations in extended cells of the electronic structure to get forces on atoms when you displace atoms in the cell sequentially, one after another. And this way you can get numerically the force constant matrix. The problem with that method is that in order to get access to K points which are close to the gamma point, you need very large cells. Because as I tried to explain last time, only K points which fall into the gamma point of the reduced Brillouin zone due to the extension of the primitive cell into that extended cell, which is actually used for the calculations. Only those points will be reproduced. So if you have a K point near the gamma point, you have to have a very large extended cell so that that point would become reduced, would become the gamma point reduced cell. So a method was developed a long time ago, actually, which is called density functional perturbation theory, which allows using primitive cells, but at the same time, it enables calculating phonons at any K point. So I will go through this method in some detail, but just give you a general picture of what is involved here. If you're interested in details, you have to look at the original literature. Yeah. So the idea is as follows. Okay, wait a second. Something happened to my iPod. Oh yeah, I know what happened. Okay. So let's start from the Concham equations. So these are Concham equations, kinetic energy operator, and this operator here is due to Hartree potential, potential due to nuclei, and this is exchange correlation potential. All these potentials contain the electronic density, and they can be written as a functional derivative of the Hartree energy, exchange correlation energy, and energy of interaction of electrons with nuclei with respect to electronic density. And that's an important point. I don't know whether that point was actually covered when you had a lecture on density functional theory and Concham equations, but this is a kind of essential. So it is essential to realize that that kind of functional derivative enters actually this operator which appears in the Concham equations. We will use this later on. The total energy is a sum of different terms. So this is the kinetic energy, and these are Concham orbitals which appear in the expansion of the density, electronic density, over all occupied states. This is the Hartree energy, exchange correlation energy, the same guys as here, interaction of electrons with nuclei, and a constant term, not a constant term, but not depending on the electronic degrees of freedom, nuclear energy. According to the Hallman-Feynman theorem, the first derivative of the total energy, this one, with respect to atomic positions, is given by that expression. So what it is, it contains here a term which is the sum of all states, and the matrix element here is taken with respect to the full potential, that one, acting between electrons and nuclei with respect to atomic positions. Of course, it does depend on the nuclear positions. It also contains a derivative of that term, nuclear-nuclear interaction term. And this is a great advantage of the Hallman-Feynman theorem, that the terms associated with the derivatives of the wave functions themselves with respect to atomic positions cancel out and do not appear. That's why the calculation of the forces is so easy. But if we want to calculate vibrational frequencies, the situation is more complex. So if we take the second derivative of the energy with respect to atomic positions, so I use C for the atomic positions for brevity, I would, of course, will need to differentiate again this term, which is here. But then I will have to differentiate that term. And in that term, there are two terms which actually depend on atomic positions. This is electronic density itself and that derivative of the potential with which nuclei act on the electrons. Taking the second derivative of that potential, no trouble. We can do this. This is just a sum of certain Coulomb and pseudopotential terms, so we can differentiate it explicitly and calculate these integrals in the basis set we have. However, we also need to differentiate the electronic density, so we will need to deal with this term. And in that term, we have to work out that derivative of the density with respect to atomic positions. Of course, once you move atoms around, the electronic density changes, and we would like to know what is the linear response to that change of the electronic density. Electronic density is composed of quantum orbitals, and quantum orbitals are solutions of the quantum equations. So if we move atoms, this operator changes, that changes the orbitals. So this is how it works. So let's have a look how the operator, this G, changes when we change atomic positions. So we change just one atomic position because we would like to calculate just one derivative, yeah, one partial derivative with respect to particular atomic position. Okay, so let's have a look what G is. First of all, there will be change of this electron nuclear potential, which is easy. And also there will be change of these two guys. But these two operators, they do not depend on atomic positions explicitly. They depend only on electronic density. And electronic density depends on atomic positions. So in order to calculate the change of that operator, what we need to do, we need to work out, we need to integrate over whole space. And so this is the chain rule, basically, written in functional derivatives language. So you have a derivative of that term with respect to electronic density times the change of the density itself. Yes, that derivative of the electronic of these two operators with respect to electronic density can actually be worked out. For the Hartree term, it's just simple Coulomb potential. For the exchange correlation term, okay, that derivative, for example, in the case of LDA, which is local in the density, it would give us the delta function and the just ordinary derivative of that function V exchange correlation with respect to the density. So that function is some function of the density. It's just ordinary function. If you looked at various density functionals, you will see this, but we're talking about LDA. And LDA is just a simple function of the density. So that derivative is just a function of space, y, the density, and that integral due to the delta function is calculated immediately. And what we arrive at is that derivative of that, of this G, so if we divide that delta G on that change of the atomic position, will be given by the derivative of that term. Then there will be a contribution due to this Coulomb Hartree potential, which appears like that. And also there will be a contribution due to exchange correlation potential. And again, we have divided by delta C, sorry, and we will have that term. So what you can learn from that is that if we shift an atomic position, the derivative of the operator in the quantum equations can be related directly to the derivative of the electronic density with respect to this atomic position. Okay, so how can we find that derivative? Let's write the change of the density. And the change of the density, because the density is this sum of the squares of the functions. So the linear change, we're only interested in linear change because we're calculating the first derivative. And the linear change would look like this. So the orbital and the change of the orbital. Now, how we can calculate the change of the orbitals? Just step-by-step calculation, as you can see. You can use the first order perturbation theory. In the first order perturbation theory, if you change the potential, and this delta G is the change of the potential of our differential equation, of the Schrodinger equation, the change of the orbital or of the eigenvector is obtained as an infinite sum over all eigenvectors of the unperturbed equation. So this lambda prime sums over all occupied and unoccupied states available to us with the particular choice of the basis set we have. So we have these matrix elements of this delta G divided by the difference of the energies and the unperturbed function. Okay, so all these unperturbed functions correspond to the Kohn-Sham equation for that given arrangement of nuclei. Yeah, and we sum over occupied and unoccupied states. Right. From that, if you divide this by delta Xi, delta, you will have derivative of delta Xi and derivative of delta of the orbitals, Kohn-Sham orbitals, and you arrive as a set of two equations to determine this derivative. So that derivative which we require for calculating the force here can actually obtain from here. So that's the idea. You see these are coupled equations which are solved in practice using some kind of cell-consistent procedure, but it gives access to the change of the orbitals and therefore to change of the Kohn-Sham potential and therefore to the forces on atoms. Yeah, and that procedure doesn't require having cells of extended size. The calculation can be performed just on a primitive cell, and you can do the calculation for any K point. You just need to generate a special normal coordinate which would excite a phonon of a particular K vector. Yeah, and that would be our Xi. I'm not going into detail here. There's quite a lot of details. If you look at the original papers, you will see that. But this is basically an idea of the method. The efficient implementations exist in different codes. Symmetry of the crystal can be used to simplify calculations. And basically, that's the idea of the method. All right. Okay, so these are the methods which one can use: frozen phonon, perturbation theory, density functional perturbation theory, for calculating phonons at zero temperature. There's one application, one more method I would like to describe to you, which is based on molecular dynamics. It requires a little bit of algebra, so I will try to just give you a quick go through this. What's time? Oh, 20, yeah, that's fine. First, we need to, so we are doing this entirely classically. The quantum consideration of phonons will come next, but just if we do molecular dynamics is a classical technique, right? You calculate forces on atoms using quantum mechanics, but you use an adiabatic approximation in which nuclei are fixed, and for each nuclear position, you determine quantum mechanically electronic structuring forces on atoms. However, the rest of it is entirely classical. Yeah, so, and we run molecular dynamics, we do a classical calculation with forces calculated quantum mechanically. So the first point which we need to see through is that the Hamiltonian of the harmonic system. So here is the kinetic energy, and this is the vibrational energy in the harmonic approximation. I, J are degrees of freedom. So that Hamiltonian can be written as a sum of independent Hamiltonians associated with normal modes. This seems reasonable. If you have a harmonic approximation, then in fact the problem is equivalent to a problem of the number of independent harmonic oscillators, the same number as the number of degrees of freedom, written for special collective coordinates of the whole system, which are called normal coordinates. I mentioned this already before. but we didn't look at the way the Hamiltonian can be actually shown to split up into the sum of independent Hamiltonians. So here on this slide, I'll show you the main steps in getting this. So first of all, we introduce these normal coordinates, the same as we had before when solving the harmonic equations of motion. Here, M are masses, U atomic displacements, and this Y lambda are eigenvectors of the dynamical matrix. Okay, and I showed to you, I think, that the potential energy, that one which is here, if written via these normal modes, has this sum of terms over each phonon mode. These omegas are phonon frequencies. Okay, so it just looks like a sum of independent elastic potential energies associated with each phonon. What we need to do is to consider now the kinetic energy. For that, let's differentiate that expression with respect to time. We arrive at this one, then we multiply by that expression. So we have Y lambda, but J component of the eigenmode, and we sum over lambda both sides. So the algebra is here, but what is important for us, that little trick allows us to solve for these atomic velocities and express them via velocities of these normal modes in that way. Correspondingly, we can now have a look at the kinetic energy. And the kinetic energy is the sum of these U dot squares. And if we now plug these expressions in here and look and use orthogonality of the eigenvectors of the dynamical problem, we arrive at this. So in terms of normal modes, the kinetic energy is also is a sum of independent kinetic energies of unit masses associated with the normal modes over the normal modes. In fact, taking this term as the potential energy, taking this term as the kinetic energy, you can clearly see that the Hamiltonian is already in kind of a form we would like to have for of a set of independent harmonic oscillators of unit mass. But okay, if you're really very strict with mathematics and physics, you have to consider the Lagrangian, like this, kinetic energy minus potential energy, and then work out the conjugate momentum to the new degrees of freedom, which are these normal modes. And this is obtained by differentiating Lagrangian with respect to velocities of this new modes. And you obtain Y lambda dot. So this is actually a square of the momentum. Yep. So now you can relate the old momentum and so the old momentum, which are U dot times the mass, which are this, and the new momenta, these ones, and write the total energy of the system, the Hamiltonian, in the following form. And this in this expression, you can recognize that the Hamiltonian is the sum of independent Hamiltonians for each normal mode. So there is no cross terms anymore. So all this quadratic form of displacements and momenta is completely diagonalized. So our Hamiltonian in terms of normal modes is the sum of the Hamiltonians. We call them little h lambda. And now with this little exploration in the normal modes, we can try to show to prove the following formula. That formula states, it is written here that if I calculate the correlation function, momentum correlation function for all atomic displacements, and I have for all atoms, basically, for all degrees of freedom, and I have this 1 over mass prefactor, that is that Fourier transform of that quantity is equal to this. And if you look at that, the beta is 1 over kT, temperature, inverse temperature. But what you have here is the density of state for phonons. And this is a very interesting observation because doing molecular dynamics, you can actually get the vibrational frequency of phonons. Yeah? And this is an example of that. this molecular dynamics of water, and you can see there's some peaks in this correlation function at the frequencies associated with the frequency of water. Of course, this is a finite temperature calculation, so it goes beyond the harmonic approximation in molecular dynamics, and therefore these peaks are not delta-like peaks. These are wider, but at least that way you can see where the frequencies might be. So let me give you just a quick derivation of that result. So what we are going to do is this. First of all, we will try to solve explicitly Newtonian equations of motions for our system and obtain time-dependent displacements and momenta. And this is done in the following way. So this is our Hamiltonian, okay? So these are normal modes and associated to them momenta, while all displacements and all momenta. And these normal modes that satisfy each these harmonic equations of motion. So the solution of these equations can be written like that. Of course, I have to add this complex conjugate part because this quantity must be real. The constants A lambda may be complex, or will be complex actually. Yeah. So what we need to do now is to solve, to use initial conditions in order to solve for these constants. Yeah. First of all, the full displacement UI can be written via normal mode. So we just solve this equation as we did before when solving here this equation with respect to these velocities. We solve it the same way, and we can write this displacement via normal modes explicitly. And this is the formula we need to use. And in the same way, we can write momenta. So now if we place t equals 0 in these two expressions, we will get in the left-hand side initial positions and momenta. And solving then for these constants, A lambda and A lambda star, so solving these equations for t equals 0 would give us, so these are the equations, would give us these constants A lambda. All right, once we have these constants A lambda, we plug them in here, and we obtain this formula, which gives us explicit evolution of momenta and atomic displacements in time if we knew initial positions and initial momenta of our system of atoms. You see? So this is a very interesting result. Okay. So now our goal is to calculate this correlation function. You can easily see that if you calculate this, if you multiply PIT, which is given here, with PI at T prime, P or PJ, or PI, we need a diagonal one. Yeah, diagonal one, with the same index I for the same degree of freedom, but at different time, T prime. So we multiply that formula with itself, but at a different time, T prime, and time only comes in these exponentials. Then we have to do this average, these brackets. They correspond to statistical average. So if we make this multiplication of these two momenta and take the average will be actually with respect to multiplication of these initial positions and momenta. And because we have initial positions here and here, we will have four terms: momentum, average, position, momentum, position, and position. Yeah, if we multiply this with itself at two different times. So what we need to do then is to calculate the averages of position times position, momentum times momentum, and position times momentum at the initial time. And initial time, we believe the system was at thermodynamic equilibrium, and actually it remains at thermodynamic equilibrium throughout this molecular dynamic simulation. But the important point is that we know what the distribution function is for the system at initial time. It's a canonical distribution, right? And in our canonical distribution, the Hamiltonian is the sum of the Hamiltonians for each of the harmonic oscillators, which we have just demonstrated. So in the canonical distribution, we integrate over momenta and positions, but we would like to do it of, so the phase space is represented by these old positions and old momenta. But we like to use the fact the Hamiltonian, which appears in the exponent of the canonical distribution, is the sum of independent Hamiltonians for each normal mode. So that is much easier than the Hamiltonian which we would have had instead, which is this one, in which this U, the old positions are in the double sum, which is not very nice when you do the calculation, when you integrate. So we would like to change variables to these new positions and momenta, which are canonical normal modes, y lambda. That can be done at the expense of calculating this Jacobian. Jacobian is easily worked out to be 1 in that case. And then if we would like to calculate any observable quantity f, depending on the normal mode index lambda, then you would have to calculate this kind of expression. So the integration over the normal mode is just a product. So you will have a product for integrals over each normal mode, because your Hamiltonian is a sum. So exponent of the Hamiltonian would be a product of exponential terms for each of the lambda. Okay. So the integrals over all degrees of freedom actually factorize, not degrees of freedom, sorry, for all normal modes, they factorize. And you also have this partition function as well, which for a single harmonic oscillator can be easily worked out. And that's what we would need to calculate. What we are actually calculating now, these positions, momenta, and their combinations, like this. All right. First of all, if we take, instead of this f, just y lambda, because this y lambda appears in the integral here, but in h lambda, y lambda squared, of course, the integral is 0. The integrand becomes an odd function. The same for the p. So average positions and momenta, of course, are equal to 0. Yeah, and that's easy to understand. For harmonic systems, the atom oscillates around the equilibrium position, so averages would be 0 for the displacements, and the same for the momentum. In the same fashion, you would have that quantity also to be 0, no matter whether lambda and lambda prime are the same or different. If they're different, of course, the integral factorizes to the average of y times the average of p. Yeah, but if lambda and lambda prime are the same, still the integrals over y and p factorize anyway, because the energy is a sum, and you get 0. However, this is not the case if you integrate, if you calculate the average of a y lambda with y lambda prime. Of course, if lambda and lambda prime are different, the integrals still split up, and you have a product of two averages like this that will be equal to 0. But if lambda is equal to lambda prime, it's an average of y lambda squared, and that is not 0. Now, and you can work out this expression explicitly. The same for the product of two momenta. So once we have these averages calculated, what we can do, we can multiply this u with u, p with p, and you will get these expressions. We only need this one. Yeah. So the average, oh, sorry, we need all of them when we multiply p at time t with p at time t prime. We will have to calculate average of u with u, p with p, and u with p. U with p would give rise to these averages, which are all 0. So we only need actually averages of u and p with different indices, but of different degrees of freedom. And now this can be explicitly written. This is only for 0 times, so we remove this exponent, multiply this expression with index I, with expression with index j, and use this averages, which is now calculated. And this is what you will get. Once this is done, we can now finally perform the full calculation of that average, which is here, p of it multiply p of it prime use this result for the averages. The calculation is actually very simple, but it requires a little bit of time. It's a bit cumbersome, but what you get is just a sum of cosine functions, 1 over beta in front. So if you now take the Fourier transform of that result, you will arrive at this, which is a delta function. So actually, the density of states of a vibrating system, and we haven't used anything like this is a crystal, or it's an arbitrary system. It could be a liquid as well. So but in the case of a liquid, it's a bit trickier because atoms move and they change the environment. So it's not quite obvious how to introduce this harmonic approximation actually. But if you can sample movement of atoms on the time scale, which is much shorter than the vibrational time scale, which is very difficult to do in real calculations, then you can even do liquids. So this is done actually for liquids. And you can still see, because of atoms moving, there are a lot of other terms contributing to the energy. So we don't have like 3 delta-like peaks as you would expect for water molecules. We have just 2 peaks, quite wide. But still, even though molecules move around, the internal vibrations of every molecule does contribute to the Hamiltonian. And that calculation approximately gives us an idea where the frequencies are. Okay, so 3 methods. Frozen-form method, which can be used for any system, but requires large unit cells to get access to the K points beyond the gamma point. Density functional perturbation theory, which allows calculating K points, vibrations at any arbitrary K points. But it's heavier than the frozen form. Although some people, it depends. It depends. If you take very large, if you have to get access to many K points, you have to get very large cells, and then maybe a frozen form method becomes more expensive than the perturbation theory. And the third method based on molecular dynamics. Of course, if you do ab initio molecular dynamics, it's again becoming very expensive. But if you do classical molecular dynamics, that method is a good method for determining vibrational frequencies. So this was a classical. Are there any questions? Are we still 3 of us, or the third
I'm
one?
still here, yeah, but I can't think of any questions.
All right, yeah, no, I'm just asking whether the third guy is still there. I think he's not there. He's not with us anymore. He left. Is it right? I think he left.
I think they are connected, but
he's connected. Okay.
Yeah, there are also other 3 persons in the meeting.
Say again?
There are 3 more people in the meeting.
Oh, really? Okay, that's brilliant.
Yeah.
All right. So so this was classical kind of consideration of vibrations. Now let's have a look at these vibrations from quantum mechanical point of view. My first slide here is actually very, very similar to what we did for the classical case, just before this proof of momentum correlation function. Yeah, and so what we would like to do here is to show that in the harmonic approximation, the Hamiltonian of our quantum mechanical oscillators is actually sum of the Hamiltonians associated with each normal mode. So this is my Schrödinger equation for the set of harmonic oscillators. So we have this potential energy in which we sum over all degrees of freedom, and you see this is a force constant matrix as before, atomic displacements, and this is the kinetic energy. First of all, we change in the potential energy, the force constant matrix into the dynamical matrix by reducing these masses. And then we plug in here the expression for the dynamical matrix y, its eigenvalues and eigenvectors. I gave this expression to you before, last week, and we arrive at normal modes. I think we did this transformation before. So this, again, exactly the same as in the classical case. The potential energy split up into the contributions due to each normal mode, and this again y lambdas, the same y lambdas as before, expressed via displacements, eigenvectors of the normal modes, or of the dynamical matrix, and masses. Then we have to introduce the momentum operator. Momentum operator is, in quantum mechanics, is that thing, right? That derivative can be calculated with a chain rule. And then we can introduce this momentum, which will be that quantity here. Okay? Quantum mechanical expression for the momentum in new normal modes. So again, this expression, this equal to that, is precisely the same as the classical case. Yeah. But once we have this relationship between the operators of momentum with respect to the old displacement and with respect to the new displacement, if you like, this new normal modes, then the kinetic energy can also be worked out to be, as in the classical case, that's the sum of p squares. But p's are operators, of course, not just classical quantities. And therefore, we have the potential energy, the sum over lambda, kinetic energy, sum of the lambda. So the Hamiltonian of this system of oscillators, coupled oscillators, in the harmonic picture is actually a sum of independent harmonic oscillators, Hamiltonians, for each normal mode lambda. Once this is the case, it is clear that the total energy of the whole system, oh, there's no lambda here, is to be given as the sum of energies for with respect to each harmonic oscillator. And we know how the energy of each harmonic oscillator looks like. It's h omega lambda, h omega times n plus 1/2. This n is 0, 1, 2, 3. It shows the excitation number for each of the oscillators. So the energies, they sum up if the Hamiltonian is the sum of independent Hamiltonians, but the wave functions are multiplied. Yeah? So the wave function is therefore a product with respect to all lambdas of the wave functions of each harmonic oscillator Hamiltonian. This psi is the eigenvector of that Hamiltonian. And we can characterize each of these functions by its numbers. Yeah, and lambda, the excitation number of the oscillator. Let's start from the following statistics a little bit. Yeah. So what we shall do here, we will calculate the free energy of a set of such coupled oscillators. As I said, the Hamiltonian is the sum of independent Hamiltonians for each oscillator lambda, and that Hamiltonian can be written like this, where n lambda is an operator which gives, when acted on the wave function of that oscillator. So I should probably write here lambda. That would be fair. What gives this eigenvalue? All right. N lambda. So this is a population operator. For those of you who is familiar with second quantization, this n lambda operator is actually B dagger B operator of the second quantization. But for us, what is important is that n lambda operator, when it acts on the eigenstate, that one rather, of the harmonic oscillator, it gives just this n lambda, that n lambda which appears in energy, times the same wave function. So basically, this is the eigenvector problem for this operator, with the eigenvalues being these integer numbers and eigenstates the same as for the Hamiltonian for that operator. That's what we actually need. If we want to do thermodynamics on this set of harmonic oscillators, we may want to consider Helmholtz free energy. Helmholtz free energy is related like this to the partition function Z, and that partition function in quantum mechanics would be given as a trace of the operator e to the minus beta h. Okay. The trace is understood as the sum of all possible states of our quantum mechanical system, and we take here a matrix element between those states of the operator. And because the Hamiltonian is a product, is a sum of operators for each normal mode, that exponent, and these different modes, they commute. The exponent is a product of exponents for each of the modes. And so you can easily convince yourself that Z is a product of partition functions for each individual harmonic oscillator. So we need to calculate that individual partition function for just one harmonic oscillator, lambda. That can easily be done, because in that case, that trace is the sum with respect to all possible populations of that oscillator from 0 to infinity. These are these states. And when we act with this operator on that state, obviously we will have an eigenvalue of that operator, which is this, but with n operator replaced by the n number, the same number as in the sum, times the same n. So this will be a number, and n times n would give me 1. It's just a normalization of the wave function. So we arrive at the sum of these exponential factors, which is a geometric progression. It is easily calculated, and therefore we can calculate the Helmholtz free energy, and this is the result you get. So this is the so-called 0-point energy, and this is a contribution which depends on temperature. Okay, so within the harmonic picture, we can actually calculate the Helmholtz free energy of our system, accounting for phonons, and that free energy depends on temperature. And the question arises whether we can actually consider thermodynamics of crystals using this kind of knowledge. Of course, we know that crystals expand when the temperature is increasing. Yes, and this is to do with anharmonicity. If the potential energy surface was harmonic, then you would not get any expansion, because no matter what temperature is, you would simply have, in the classical simplest sense, you would simply have oscillations with a higher and higher amplitude of our system. However, the average position would always remain the same, the one at 0 temperature. However, if the potential energy surface is asymmetric, and asymmetricity means that it is not harmonic. Yes, if it was harmonic, it would not have been asymmetric. It would have been symmetric. So if we have this kind of tail towards higher distances going like that, then it is asymmetric, right? So if we have this asymmetric potential energy surface, then at small temperatures, our oscillation would be like this. At high temperatures, it would shift more towards this asymmetric wing here on the right, and therefore the average position would shift at higher temperatures to the right towards higher positions, higher distances between atoms. So one can ask a question whether one can use what we just obtained, the free energy here, due to vibrations, because it depends on temperature, to account for this effect and study expansion. So what we can do, we can construct the free energy, the total free energy of our system, as the sum of the DFT energy at the given volume, and add to it this vibrational energy. All right, and then at 0 pressure, what we can do a calculation at different volumes, and for each of for each volume, we would calculate the phonons using one of the methods we considered so far. This way, you will get the free energy as a function of the volume. And if you minimize that dependence with respect to the volume for the given temperature, and that only this term depends on temperature, right? So only this one. Then you will get the equilibrium volume for that temperature. So you will be able to get the volume associated with that temperature. If the pressure is not zero, and for finite pressure, you have to consider Gibbs free energy instead. So you have this extra PV term added to the Helmholtz free energy. And in that case, you have to minimize Gibbs free energy with respect to the volume. And the equation you will obtain will be this. So this zero is replaced by minus P. So this is the equation you will have to solve. So you will perform exactly the same calculation, but instead of setting this derivative to zero, you will set it to the given pressure. But this way you will get the volume for the given pressure and temperature. So you will be able to get access to thermodynamics of crystals. This all sounds really very reasonable, but in fact, it is a rather limited approach, because actually, this can only be performed in practice for cubic crystals, because in cubic crystals, the volume is specified by the size of the unit cell, which in the conventional representation of the cell, not the primitive cell, but the conventional cell, or you can actually use the primitive cell as well, but there is just one parameter A, which is the lattice constant, and therefore that dependence over the volume can be actually done as a dependence over this lattice constant, just a single parameter. So that calculation can be done then, and I will show you an example of this, a few examples actually, for a general crystal structure, this is not that straightforward. A crystal structure is specified generally for a very general unit cell by 6 parameters: A, B, C, the sizes of the primitive cell, and angles alpha, beta, gamma between the primitive translations. And then it's very difficult to perform this calculation in practice. You have too many parameters. So you have to build a dependence of the free energy with respect to all these 6 parameters. And then for all values of those parameters, you have to calculate the vibrations, which becomes very, very difficult to do. But before we go into this, let me show you some other quantities where that so-called quasi-harmonic approximation, which is basically a way of using this free energy in some calculation, can be of use. Here, I'll show you from my own work a long time ago. We looked at phase transition between a number of structures of molecules. Molecules are here, DHBA called, which they form on the calcite surface. Okay, and there are 2 structures they form, so-called stripe network, in which they have 2 flat molecules alternated with 2 vertically standing molecules. So this is how the structure looks like. It doesn't really matter what it is. With a dense network, is another network in which molecules are all stand upright. Okay, in this structure, the molecules are bounded to each other with hydrogen bonding. Here, it's a bit more complex. But the idea here of this work was that to show how this transition actually happens. What the experimentalists observed is that initially, when they deposited molecules on the surface in vacuum, it's all in vacuum, the stripe network is formed first. And then if you increase temperature, the dense network is formed instead. So, it was important to understand for us what is the actual mechanism behind this. I'm not going to talk about the mechanism, but I will show you simply, I will illustrate you this graph in which I show the free energy of 4 systems. So this is the free energy as a function of temperature of the stripe network. This is the free energy of dense phase. But there are also 2 other free energies. And these were actually very important in understanding the actual experimental results. So the first one, marked D, is the free energy of a gas of dimers on that surface. All right. And the M is a free energy of the gas of monomers on that surface. So how one can calculate all these 4? for the striped and dense network is kind of easy. You place molecules on the surface, you identify what unit cell is, and you calculate vibrational frequencies of the whole system, including some top layers of the surface itself. Once you have the vibrational frequencies and you have the DFT energies, you just add them up together and you have free energy of the whole system as a function of temperature for each phase. All right. But what about dimers and monomers? These form a gas with these dimers and monomers moving almost freely on the surface at these temperatures. So there's another quantity to the free energy, which is called configurational entropy, which is an entropy due to which is the contribution to the free energy due to the entropy associated with the possibility of these molecules occupying different lattice sites. Yeah. So if you do a combinatorics for dimers and monomers, you arrive at that contribution to the free energy, and you can relate this to the coverage, which is a number of molecules per number of sites. And this is different for dimers and monomers. So the total free energy would then be equal to the DFT energy, vibrational energy, as I described. And for these dimers and monomers, you also have the vibrational energy. You place in your calculation a dimer on the surface with some unit cell, and you calculate the total vibrational energy, and you subtract it from the vibrational energy of the surface itself, because you're interested in the different, interested in calculating this per dimer, the change. And you have this configurational entropy as well, and then you have these plots given. So you see this vibrational free energy comes as a contribution to some other terms, and that was very interesting to understand, because the stripe phase, which is formed first, cannot be explained unless you assume that dimers were initially. And dimers were initially because the molecules formed dimers as they evaporated from the crystal in the experiment. They evaporated from the evaporator somewhere and then kind of fly as a gas into the chamber where the actual sample is, and they form dimers there. So it was a pivotal to understand the experimental results, to realize that when the molecules fly on the surface, they don't do this as monomers, but do this as dimers. Because if we did it as monomers, the monomer is the most favorable structure. There will never be formed any crystal structures at all. But they fly as dimers, and they form then a dimer phase, which is this stripe phase. And after that, with increasing temperature, given molecules a bit more thermal energy, they form a dense phase, and if you increase the temperature even more, then the dense phase breaks up. So now a bit more to the point of vibrations. Shall we make a break, a few minutes break? Yeah?
Yeah, I would be okay with that.
Yeah. Let's do a few minutes break. Yeah. Karen, are you there? No, so the recording will continue, I suppose. I think we can continue, right?
Yeah, I think so.
How many? Let me stop sharing to check how many participants we have currently. Oh, we have some. Okay. Oh, where's my screen? That's strange. Disappeared. Huh? Wait a second. What happened? Okay, it's here. Ah, now it's here. That's very strange. Ah, I know what happened. I think it's my screen was behind that one. It's kind of analyzing the screens, different windows on the screen, and this is how it makes the choices. That's interesting. So it does it on a visual kind of way. Right. So this is another example of gray tin to white tin phase transition. So at low temperatures, it's FCC diamond structure, but at 13 centigrade, it undergoes a phase transition into the body-centered tetragonal structure. Yeah, and that transition has been described in a paper, in this Pavone paper, it was a long time ago, 2001, using so-called naive quasi-harmonic approximation. So what I described for this work, it was also naive. We didn't recalculate phonons at different temperatures. We used the phonons calculated at 0 temperature, at the first structure. This is what these guys did in their paper as well. They calculate phonons for both structures separately, and work out the quasi-harmonic free energy, and then simply plotted the free energy as a function of temperature for both structures. So here you can see for the alpha phase phonons and for the beta phase phonons. And what is interesting to note is that alpha phase phonons go to much higher frequencies than the lower phase. Here is like 140 inverse centimeters, the highest. He is over 200. So if you look at the density of states, so this alpha phase has these peaks here at high frequencies. And because of that, the contribution of phonons due to beta phase as compared to the alpha phase becomes larger. And in the free energy, the entropic contribution is subtracted. So as the temperature goes higher, that term becomes bigger and bigger. So, but basically what you do, this is the qualitative explanation. What you do in an actual experiment, you simply add this vibrational energy to the DFT energy for both structures separately. And this is what you get. The energies, DFT energies, just go like this. You can't see any transition. But if you add these vibrational energies, the free energies go down because the contribution due to vibrations always going down like that with increase of temperature. But they go down at different rate. And therefore, at some point, they cross. And that point is actually very close to the experimental 13 degrees centigrade. Yeah. So at temperatures lower than that, beta phase is higher. So alpha phase is lower. So you have this phase as more energetically favorable. But after that temperature, beta phase actually wins the race. Yeah. So this was a naive harmonic approximation. What they should have done is for each temperature, they should have obtained the equilibrium structure. They should have obtained the actual volume. In both cases, you have no, in this case, you have a cubic structure. In this case, you don't. Actually, this is not cubic. So there are more parameters you need to specify for the unit cell. So what they should have done is for the cubic phase below the phase transition, they should have recalculated phonons and therefore the phonon contribution to the free energy for each volume of the crystal, and then that would be the full harmonic, quasi-harmonic approximation, and then work out the dependence of the free energy on the volume. This for the alpha phase. On the temperature, sorry. But for the other phase, they should have considered all possible configurations of the unit cell. And then for each of those, calculate the DFT energy and calculate the phonons, and therefore then plot the free energy for at different temperatures for the minimum free energy at each particular temperature, which is quite a task to do. Yes. So I haven't come across any paper where people actually have done this for very complicated structures because its computation is just very demanding. So here is another work published in 2007, in which they looked at cubic structures, and they considered phonons as a function of temperature for different structures. And they considered, therefore, thermal expansion. And because the structure is cubic, they were able to perform all these calculations I just described. But they also looked at various other features which may affect the calculation. They very carefully considered cutoffs. So they needed to do this. They also very carefully considered the unit cell size. They used frozen phonon approximation. So they were very conscious of what kind of unit cell extension one has to take in order to have enough K points the free energy, because the free energy would, in the end of the day, be a sum of the K points. They looked at different density functionals. They actually also looked at anharmonic contributions to the free energy and the role of defects. So I'm not going to go through this, but what is important nowadays, it is possible actually to use this quasi-harmonic free energy calculation for simple structures and perform the whole calculation and do all the actual crystal thermodynamics. And then they worked out the expansion coefficients, which are plotted here. Okay, so where am I? All right. So what can we do instead? So we just looked at different methods. We have good methods for calculating phonons at 0 temperature. Frozen phonon, time-dependent perturbation theory. We have some methods at non-zero temperature, which is molecular dynamics. For crystals, it's okay. it will give you these frequencies, but what if there are several modes close to each other? Then you will have the peaks due to these frequencies actually merge with each other. So and this is molecular dynamics, it's a numerical technique. So yeah, I'm not sure whether this would be possible to actually make this method very, very explicit and precise. Also, how to get the frequencies, how to associate your vibrational frequencies with different K points is also not quite clear. And also, but frozen phonon method allows you doing that. However, you need to take very large cells sometimes in order to get access to K points, which are close to the gamma point or are in some very general positions. So these guys, they came across it's also based on molecular dynamics. So of course, it has these disadvantages that if you want to do this ab initio, then you have to run ab initio molecular dynamics. But in principle, this method actually can get you vibrational frequencies and then the free energy as a function of temperature, taken into account even anharmonicity effects. So so if you have non-zero temperature and non-zero pressure, what can you do? So this we have just covered. DFT plus quasi-harmonic approximation. It has some advantages, some disadvantages. There is another method, analytical method, called self-consistent phonons, which was quite popular in the past, but it's rather expensive. And as far as I know, no implementation of this code within DFT or within any kind of platform exists. Maybe it does, but I haven't heard of it. Velocity-velocity autocorrelation function, which we considered before, works at finite temperatures, but it requires running molecular dynamics over long times, and this may become quite difficult. And also, you have to, if you want to get frequencies at different K points, you will have to make an expanded cell. So run molecular dynamics simulations for large cells, which is also difficult. If you would like to include harmonic effects, you have to do something like a thermodynamic integration. So it is also a rather complicated solution. So this method allows you to run calculations. So it's called temperature-dependent effective potential method. So it is based on ab initio. It can be based on ab initio. Includes naturally anharmonicity, can run at finite temperatures, and can be extended to any lattices, not necessarily only cubic lattices. I will give you on that single slide just some idea of that method. So suppose you're given a structure, you have no idea what the structure would be, or you're given a crystal of some structure, and you have no idea what this structure would be, completely unaware, it's a new system to you, what the structure would be at the given pressure at the given temperature. What you can do, you can run an NPT molecular dynamics simulation to determine what the structure is. So you run an NPT ensemble molecular dynamics simulations, ab initio simulations, and by looking at the averages for cell structures, this will be all run in periodic boundary conditions. So by looking at the averages of your cell, so your cell is a function of time, would somehow fluctuate around different positions. For example, the cell size, the angles between the primitive translations, and so on. So you will be able to get averages for your cells, and by looking at those averages, if you have enough sampling in your molecular dynamics simulations, you can get an idea what the structure would be. Is it cubic? Maybe very close to cubic, or maybe it's tetragonal, or maybe some other. So the point is that for the given pressure and temperature, you can determine using that method. It won't be exact, but it will be some way of getting a structure for these particular conditions. So then you take these average values and run NVT calculation instead. So molecular dynamics NVT calculation. So you fix the structure, the cell, but you allow atoms to move around by molecular dynamic means. Of course, the atoms would move around their positions associated with this pressure and temperature. And that structure could be very different from what we would get if the temperature was 0 and we relax the whole structure with DFT. But the total potential energy of our system would still consist of 2 contributions. There will be one contribution associated with atoms being at their equilibrium positions. And that will only depend on temperature because the equilibrium positions depend on temperature. But there will also be a quadratic contribution due to atomic displacements out of these equilibrium positions. There will be no linear term because, again, the equilibrium position it gives no linear term, even for this extended cell. Forces on atoms would still be 0 in the extended cell if atoms are in equilibrium positions. Oh, give me a second. Алло, Ника, у меня сейчас лекция. Потом. All right. So there will only be a quadratic term. This will be displacements, vector of displacements of all atoms from their equilibrium positions at that temperature and pressure. And this will be a matrix of some coefficients. This is an analog of the force constant matrix. So if we have a way of determining this force constant matrix from our molecular dynamics for the given pressure and temperature, we would be able to diagonalize that matrix with masses, all done properly as we did before, and calculate the vibrational frequencies, which would be associated with this particular geometry, which is equilibrium geometry for this given pressure and temperature. And once we get these vibrational frequencies, we would be able to work out the total free energy of our system for these thermodynamic conditions. How is this done? So when you run these NVT simulations, you have over time, so this is time, vector of atomic positions as a function of temperature. So at each time step, you will have a long vector of all atomic displacements from this equilibrium position, right? But at the same time, you will get the same vector of forces acting on atoms, associated with these displacements. These forces and displacements must be related via this matrix phi, as in the 0 temperature case. And therefore, the idea is follows. On the one hand, the forces should be related with the displacements like this. On the other hand, we know what the forces are from our DFT runs at each time step, which are here. So we'll try to minimize that error function. Here we sum over all time steps, where we believe the calculation already converged and become an equilibrium simulation. So we have to wait a certain time to equilibration, but after that we run a production run and we sum up these differences of the forces given by DFT on the one hand and the forces we expect from the given unknown yet this force constant matrix. Right, there is a way to determine this phi, which is called Moore-Penrose pseudo-inverse. Yes, it's like minimizing this quantity with respect to those elements, because imagine the number of elements here is actually finite. This is a finite matrix, for the given unit cell, but the number of these forces and displacements is actually very, very large. We have very many time steps. So if the size of this matrix is n by n, but of course, this matrix is symmetric matrix. So the total number of elements is 1/2 distinct elements, 1/2 n times n plus 1. But the number of these vectors, each vector is of length n, but the number of these quantities is n times the number of time steps we have. This is huge. So it's like a mean square procedure. You determine with this Moore-Penrose procedure the best phi, which would give this error function the smallest possible value. All right. But once you have done this, you determine this best coefficient from the molecular dynamic simulations. And this can be done for any structure. It can be cubic, it can be tetragonal, it can be hexagonal, whatever. It doesn't really matter. As if you have the structure well determined from your NPT simulations, you can basically do this, yeah, in practice. Then diagonalizing phi or constructing the dynamical matrix for this phi matrix and determining the vibrational frequency, you can calculate the corresponding contribution to the free energy from those vibrations, as we did before. But this will be on top of that energy U naught here. So the total free energy, which also depends on temperature. So the total free energy would be vibrational energy and this U naught. How can we determine this U naught? We know what is the potential energy is of our system at every time step. This is that energy. DFT code does give us this energy. Okay, but that energy contains that elastic contribution as well. So if we subtract this elastic contribution with no displacements for each time step, we know what precisely displacements are, and the update matrix phi, if we subtract this from this U, we will get this U naught. And if we sample this with respect to all the run molecular dynamics run, we will get this U naught for the given structure. Then we change the temperature. We run again NPT simulations for the new temperature or pressure, and we again determine the shape and the size of our unit cell. Then we run NBT simulations for that cell fixed at that size and shape, and we repeat this procedure. And this way, we will get the free energy and the vibrational frequencies. And the guys in these papers just demonstrate the power of that method on two systems. There are many more simulations they have done, but this is quite impressive. Look at this lithium. Lithium, if you calculate vibrational frequencies of lithium at 0 temperature, they're actually imaginary frequencies. So if you take lithium, relax with DFT, yeah, the total energy, and then calculate frequencies, you have imaginary frequencies. The same for this zirconium. You have imaginary frequencies. However, if you run their methods, you don't have this problem at all, and you have a comparison, very good comparison with the experiment. So this is quite an interesting idea, which you should actually have in mind. Okay, that method is quite general. It is numerical, of course, but it's quite general. It is applicable to any structure. It can be done on an ab initio level as well. Yeah, and it gives access not only to the structure of the system at given thermodynamic conditions, but also to the free energy and the vibrational frequencies at these conditions. It allows you to avoid problems of soft modes and imaginary frequencies, which is actually a problem with other methods. All right. So the last thing I wanted to consider, as I may have promised last time, last week, is to show you that when you do kinetics on systems, you actually also come across vibrations. That's another application of vibrations. And what basically I would like to derive for you is that formula. This formula at the bottom, which shows the transition rate of a system from one potential energy minimum to another potential energy minimum. Suppose you have a potential energy minimum. We discussed this last time. You have one minimum, another, and you may cross over from one to the other. And you would like to find out what is the rate of crossing from one minimum to the other. So if you are interested in simulating melting processes or crystallization processes or chemical reactions of any sort, you would need to consider rates. If you would like to know how the reaction proceeds in real time, you need rates. Sometimes rates are also needed to explain phase transitions or different, if you have many competing processes, why that particular outcome comes out of all these processes, why not the other. You will need to calculate these rates and see how the reaction proceeds. Yeah. So in that formula, you have an exponential factor which has the difference of two energies, one at the bottom of the starting potential energy well, when the system is initially, and the potential energy at the top of the crossing. So at the so-called transition state or saddle point of the potential energy surface along the minimum energy path between one minimum towards the other. But the prefactor is what interests us here. Prefactor contains a ratio of vibrational frequencies. At the top, you have all vibrational frequencies of the system at the minimum of the initial potential well. At the denominator, you have vibrational frequencies, all real vibrational frequencies multiplied at the saddle point. And the vibrational frequency, which corresponds to the vibration across the saddle point, which actually is imaginary, which must be the case for the saddle point. I might have explained that last week. I can't remember if I told you about this or not. But in the saddle point, in the direction across the barrier, the potential energy actually has a maximum rather than a minimum, and therefore the eigenvalue of the dynamical matrix here, omega square, which is an eigenvalue, will be negative. It will be real, but will be negative, and therefore omega itself will be imaginary. So that frequency is not included here. So you have only frequencies, all other frequencies, which all will be positive, real, positive. And in the numerator, you have all the frequencies without exception, but at the minimum. Okay. So this is the so-called Benard formula. And what I'm going to do now is to derive you this formula. Very qualitatively, we have like half an hour for that. Maybe I'll finish earlier. I will not go into all the details. I don't know if there is, I have actually a very detailed calculation on which these slides are based. And I don't know if on the website, TYC website, this file is placed. Do you know?
I saw there were like a lot of videos that were optional.
Do you know there's a detailed derivation there on the website?
Let me check.
But never mind. If somebody would really like to learn this properly, I can send you directly the file. But let's start from a very
it seems that they are in the website. Transition rates, right?
Yes.
Yeah.
Yes. So it is there. Okay. Okay. Good. So what we're going to talk about is so-called transition state theory. Yeah. Let's start from a one-dimensional case to understand what we're dealing with. So suppose we have a potential energy surface. Our system initially is here in the minimum of the initial state. And there is a final state somewhere here. But what is important for us that there is this transition state that at the top of the barrier. Yeah. And if we would like to learn what is the rate for our system to cross that barrier and go from the initial to the final state, we actually need to work out how probable is to get our system at the top of the barrier here with the velocity of the system directly towards the product basin. Okay, because if the velocity is directed that way, the system would fall back to the original basin. Yeah. So I describe my system is a classical consideration altogether. We're not going to the quantum mechanics at all here. It's much more complicated with quantum mechanics, much more complicated. It's a kind of several orders of magnitude more complicated. So the classical consideration, it goes like this. So we have the Hamiltonian, which is kinetic energy plus potential energy, depending on this x. Right, and let's work out the probability to find our system at any point x on that potential energy surface with some velocities v. According to the canonical distribution, this will be a product of two probabilities. This px will be given like that. So it's a potential energy part of the canonical distribution with the potential energy here. And zx would be the corresponding partition function. And we integrate here within over all x within the basin. So from minus here with x naught somewhere in the middle, up to that point xb when we have this saddle point. This PV dV would give us the probability to have velocity between v and v plus dv for our system. All right. So P of v is a probability density actually. Yeah. And that PV is the Maxwell distribution, of course. So if we would like to learn what is the rate, we need to find the probability to find our system precisely here at that top of the at the saddle point. So at a value of x equal to xb. Right. The total flux of our system to reach that point will then be equal to this expression. So we have v here because this relates to the flux, and we integrate over all velocities from 0 to infinity. From 0 to infinity, because we want all the velocities directed to the right, as I explained before. So that calculation can be easily done. We can integrate over the velocities. This PV is the Maxwell distribution, so we need to work out this integral, and that calculation can easily be done. So partition functions for the velocities is the same as for the Maxwell, so you get this V average very easily. Then we need to analyze this this potential energy part of the distribution. For that, we'll expand our potential energy around that minimum in the harmonic approximation. That would be ux naught plus the harmonic term, x squared. That expression would allow us to work out the partition function zx. And when doing this calculation, of course, because of this exponential term with minus x squared here at the top, we integrate initially from 0 to xb. We can easily extend this integration from minus infinity to plus infinity, because that exponential term would at this point be almost practically 0. And when we do this, this can be done analytically very easily. And it will give this exponential term with the energy at the minimum of the initial basin. So that is about Zx. Now we need to work out that P at xb, at the saddle point. And that calculation requires calculating this exponent with the potential energy at that point, at the saddle point. This is easy to do, because that energy would simply be ux naught plus the barrier between the two. So now we have this uxb, therefore we can calculate this exponential. We have zx, this one, so we have the full access to that one, and we have the factor of the average velocity, which is here. Combining all these results, we now get the rate for this one-dimensional system, and this is what it is. So here in the exponent, we have only the barrier. This is the Arrhenius formula, yeah, with the 1 over kT and the barrier in the exponent, but here as a prefactor, we have the vibrational frequency of the system in the initial basin. And that formula is easy to understand. My system vibrates here, and each time it has that many, at each second, it has that many attempts to cross the barrier. And at each crossing, it has that probability to cross it, which decays exponentially with the barrier height, and it increases exponentially with temperature. Yeah. So it's a product of these two contributions. So on the one hand, it's very difficult to cross if the barrier is high, but on the other hand, you have this many attempts to do this. And these omegas, this of the order of the vibrational frequencies. So they're 10 to 13 inverse centimeters. Oh, sorry, hertz, 10 to 13 hertz. That is the frequency with which atoms vibrate. It's a characteristic frequency of atomic vibrations. So that quantity is very large, actually. Yeah. All right. So this was a one-dimensional case. So of course, the question is, how can we generalize this simple consideration to a general system? So this is what I'm going to demonstrate to you now. So we need to consider the full multidimensional potential energy surface. So we have one basing here. This is initial basing of reactants. There's another basing, the final state, which is a basing of products. And somewhere in between, we will have a surface with 1 degree of freedom less, which is called dividing surface. And somewhere on that surface, there will be this saddle point. So my transition minimum energy path, if you like, would start here, would go somehow through this saddle point and arrive at the minimum of the product basin. I can introduce a function f as a function of all this multidimensional space, such that it would be positive everywhere on the right of the dividing surface, it would be negative everywhere on the left of the dividing surface, and would be equal to 0 on that surface. And also, I will make sure that this function is such that it's equal, that its derivative along the direction perpendicular to the surface is 1. Then we can consider a flux of our system. So our system is atoms on that potential energy surface. Each atom has a velocity. Yes. So the flux through that dividing surface, somewhere at some coordinates of that dividing surface, somewhere, will be given by this expression. So you should recognize this, because NV dt would be a number of particles coming through a unit surface over time dt, and would be a concentration of these particles. We're talking about one particle, because our system is one particle, so there's no n. So we will have this expression. ds is a unit surface here. dt is time, and vn is the multidimensional vector of the velocity dot product with a normal, multidimensional normal to that surface. And that multidimensional normal is given by the gradient of our function, f. Okay? We don't need to know what that function is. It could be any function satisfying the conditions I just described. That's the interesting thing about all this. The explicit form of that function is not required. The total flux over time delta t will be obtained if we now integrate that expression with respect to all points on the dividing surface and with respect to all velocities of our system, of all our atoms. So these are multidimensional integrals. So now I plugged in n as a gradient. I introduced the probability, as we did before, the canonical distribution for our system to be on the dividing surface. This qs corresponds to this ds integral velocities, and I also put a heaviside function, which states that only velocities such for which this dot product with the normal to the surface is positive would contribute. Yeah, so this is analog to the fact that we used here, that the integration is performed only over positive velocities. So here, in the multidimensional case, velocities may be directed and not necessarily normal to the surface, but as long as the dot product of them with the normal is positive, they will remain, they will cross the dividing surface and remain in the product's basin. If the negative, they return back to the initial reactants basin. Yeah, so that's why we introduce this Heaviside function. The probability, that probability is given by the canonical distribution in the same way as before. So we have here the full Hamiltonian in the exponent at the dividing surface somewhere. And this is our partition function, in which I have another Heaviside function, because we take the partition function assuming the system is in the reactants basin. So we only integrate over all values of the all parts of space where this minus f is positive or f is negative, and f is negative only in the regions of space of the reactant basin. Okay, the last step which I can introduce is to replace this surface integral over this dividing surface with the volume integral over all space by introducing this delta function. The delta function would cut out all the q values which are not on the dividing surface, because as long as f of q is not equal to 0, the delta function is 0. Right, so we arrive then at the rate, which is flux per unit time, at that expression. This is the basic transition state theory expression for the rate. And people use this expression basically in some way and form to work out the rate in classical molecular dynamics simulations. You won't be able to do it ab initio. Okay, I'm not going to go through this Chandler correction, which is basically a correction due to the fact that even if you cross the dividing surface, you may still return back via kind of special trajectory into the reactant surface. And using some specific molecular dynamics simulations, you can work out what this correction would be. But this is not our concern right now. Okay, so we worked out this rather complicated integral. It contains integration over whole space of molecules, these Q integrals, now also velocities. What is interesting about this expression, that velocity contribution can be integrated out exactly. Yeah, so I'll show you the idea of this result. So first of all, let's have a look at the numerator and the denominator, these velocity integrals there. Okay, so here I just show the terms which are associated with the velocity, because we integrate over the velocity only. And therefore, in the exponents, we have kinetic energy only, and kinetic energy is, of course, the sum of the kinetic energies of each atom, of each degree of freedom. We introduce massless velocities, as we did in molecular dynamics, actually, something similar. In this case, the kinetic energy doesn't contain mass at all. So this V tilde are massless velocities, and the kinetic energy is simply V squared over 2. Yeah. Then the integration of the velocities is performed instead of initial velocities with respect to this massless velocities. This would give out this Jacobian before. The kinetic energy contains this massless velocities squared. Now, this term here, I'll introduce this vector EQ along the normal, but with the mass. So this the mass contribution comes from replacing V with V tilde. So this term is the same as this one. And this Heaviside function again appears like that. Then there is a very fine trick. Yeah, the trick is that okay, where is velocity in this integral? Velocity comes in here, here, and here. But if you look at that term here, the velocity comes as V squared. And if you rotate space, that V square expression is actually remains invariant. Therefore, if you rotate space in such a way, that the first component of your rotated velocity would be exactly parallel to the normal. All others will be non-parallel, perpendicular to the normal. Then what will happen? First of all, you can work out the Jacobian. Jacobian in that case will be 1 because you just make a rotation. This term contains the dot product of these rotated velocities and the normal to the surface, the dividing surface. So it will basically be just V1, the first component, which is along that normal. Yeah. So only V1 would contribute to this Heaviside function. Before we had a dot product. That's why we did the rotation. That dot product would simply be V1 as well. And in the exponent, we will have V square of the rotated velocities. So as you can see now, we got rid of these very complicated terms and replaced them basically by these two. This would give us integration over V1 from 0 to infinity, as we did in the one-dimensional case. All other terms just factorize. We can split out our integration. We can integrate over all velocities which are not along the normal, and separate out the integral for the velocities which are along the normal. This integral is precisely the same as a one-dimensional case. These integrals are exactly the same as you would have if you did the normalization of the Maxwell distribution. So the result of that simulation calculation is very simple. It's given by that formula, which contains this normal vector, temperature, masses. Yeah. All right. So this was the numerator. The denominator is much easier. The denominator, you can perform the calculation of the denominator straight away. You don't need to rotate, and you get this result. So all in all, these two calculations give the ratio for these two analytically. I'm talking about the ratio because the calculation of the denominator actually does not depend on the position Q. And therefore, in these two integrals, that contribution of the V integral in the denominator can be taken out and then incorporated here in the numerator, and then you will deal with the ratio. All right. So after getting rid of the velocity integration, we arrive at the following expression for the rate. Okay. Now we have only Q integration over space. Still have this delta function in the denominator, which we can get rid of and replace the volume integral in the numerator with the integration over the dividing surface. So this is a new expression we have just obtained. Okay. And I should say this calculation was exact, no approximations whatsoever. Yes, so this is exact expression. And that can be used for any potential energy surfaces. Now let's see what will happen if we choose a harmonic potential energy surface. If we choose a harmonic potential energy surface, it happens to be here and here. And then we need to do this integration. And I will show you that integration can actually be performed analytically. And then it will arrive at the Vineyard formula I showed you at the very beginning. Let's start from the denominator. In the denominator, we integrate of the reactant basin. Yeah. So we expand the potential energies there around the minimum. So Q naught is the minimum point of that reactant basin, this one. So we expand the energy, and the harmonic approximation, we have this expression. This is the displacement from the basin minimum, and this is a force constant matrix. Then we do what we did before, basically. We introduce massless displacements, then the potential energy becomes quadratic with respect to them, and here is the dynamical matrix. And then we can basically integrate that denominator explicitly. So we expand over the whole space. We integrate over the basin itself initially, but because of the exponential term, this one, we can easily extend the integration over infinity, assuming that this basin spreads out to infinity. And then this is the Gaussian integral, which can be explicitly calculated by going into the normal modes. I would not do this, just showing you an idea, and this is the result. Okay. So we have done this integral. Now we have to do this integral in the numerator. The numerator integral is performed over the dividing surface, but we can use the same trick. Look, when we go over the dividing surface, we can expand the potential energy only around the saddle point, because this is the potential energy comes in an exponent, and as you go away from the saddle point, that term would go quickly to zero. So only terms in the vicinity of the saddle point would contribute, only in the vicinity here. And therefore, we expand our potential energy around the saddle point. And that expansion will look like this. There will be positive terms associated with all normal modes, which are, oh, I'm sorry. У меня лекция. Перезвони. All terms with the positive frequencies, real frequencies, sorry, these terms will all be positive. And this corresponds to the displacements of the system within the dividing surface. But there will be one term with a negative contribution. This frequency is actually imaginary. And that degree of freedom corresponds to the crossing the dividing surface. You see? So this corresponds to the crossing. So the dividing surface is here. So we have a saddle like this. Yeah. So all frequencies positive correspond to running here. But if there will be 1 degree of freedom, and only 1 degree of freedom, which corresponds to crossing this dividing surface. Dividing surface is here. Yeah. The crossing dividing surface, and that corresponds to the maximum of the energy. So you have this negative contribution. Then you can show that the model of this vector EQ is actually equal to 1. And then the integral over the dividing surface can be calculated analytically by simply using this expression and the fact that on the dividing surface, this y is 0. Because we stay on the dividing surface precisely at that point. We do not go away. Yeah, so that is 0. So we can cross out this term and use only these ones. And then when we integrate over the dividing surface, this integration is exactly the same as we performed for the denominator, but for 1 degree of freedom less. Yes. And the result is here. Okay. And now if you divide one on the other, you arrive at the Vineyard formula. So this is the idea of that derivation. It's rather long, but it is actually quite illuminating. And it shows that even for a very complicated potential energy surface, you can work out the transition rate between, but in order to do that, you not only need to know where the minimum of the reactant basin is, you need to know where the transition state is, so you would be able to calculate the barrier. You also need to know the frequencies at the basin minimum and at the top of the barrier, because they define the prefactor. Prefactor may not be that essential. And if you look at this expression, here you have all the frequencies. Here you have all the frequencies but 1. Yes, so the ratio here is of the order of the frequency associated with the degree of freedom taking you over the barrier. Because in that product here, that frequency is missing, because we didn't, that negative term did not contribute to the integral in the numerator, because y coordinate on the dividing surface is 0. So this ratio is of the order of that frequency which takes you over the barrier. And if you and there's a 1/2 pi, and let's have a look at the one-dimensional case. In a one-dimensional case, this is precisely what we got. One frequency which takes you over the barrier divided by 2 pi as a prefactor. So this formula actually is a generalization of a one-dimensional case. Okay, guys, so this basically all what I wanted to consider with you. Some general knowledge about vibrations, how one can calculate vibrations using ab initio methods and maybe classical methods, and where vibrations are utilized, yes, in calculations of the rates, this Vineyard formula, in doing thermodynamics of crystals, in this quasi-harmonic approximation, and basically that's it. If you have questions.
Hello, not exactly a question. I'm just interested about the publication you based regarding the temperature-dependent potential method.
You mean which method?
Temperature-dependent potential method.
This method of Abrikosov, this one.
Yes.
So you have references here. So this file, these slides are available on TYC web pages, so you can go and have a look.
Okay, thank you.
There are many more. So these are the two, I think, the first two. They have some more. There are a few papers, I believe, they try to work out high order elastic constants. So the cubic term in the expansion of the energy, how to include symmetry. They've done some work on this, yeah. So you can have a look.
Yeah, thank you.
Any more questions? All right, then thank you very much for attending these lectures. Thank you.
Okay, thank you. Bye.
Bye-bye.
Thank you.
Bye.
Bye.